if we have time, of course we will go through the sample exam answers and stuff like this, but they are more like a consequence of whether you understand the bulk of these reactions as a whole or you don't. Try to relax as much as you can and have a very fresh look, as if you're seeing chemistry for the very first time in your life. For some of you, it's not very hard to imagine at all. No. But try to have this a baby approach to what organic chemistry is. Like pretend to be a baby.
I wish.
So let's try with this. And there's only 10 slides, like all of the transformations can be categorized in 10 different categories. The first one is called classical substitution. See the blue ball? What does it want? To replace the green ball. The green ball will always be a leaving group, but the blue ball will always be something with the lone pair. What do you expect to happen here? Yeah. Does it attack from the back or from the same side? That's how SN2 works. It has to attack from the back. Do you think there are any limitations? If this is too crowded, if this position is very crowded, will it be hard? If those are 3 carbons, that's impossible because it's too crowded then. It has to be, at least one of them has to be a hydrogen, because hydrogens are small, so it's easy to approach it from the back side. Also, you see how there's no charges here. That's not a positive charge. There's some delta plus here, which means this has to be pretty strong to attack. If this is lukewarm and this is lukewarm, they will not do anything if both are lukewarm. But at least one of them needs to be strong. Hopefully both of them, but at least one of them needs to be strong. Yes, inversion of configuration, that's what we expect. It cannot be tertiary, it cannot be too crowded. What does it mean it has to be sp3? What's a different word for sp3? Tetrahedral, right? The carbon has to be tetrahedral. It cannot be at a double bond, it cannot be at a triple bond, it has to be a tetrahedral carbon. And yes, the blue ball has to be charged, so water, the neutral water, is just not strong enough to do SN2. But if you make it O-, like OH-, for example, yes, then it's strong enough. If it's neutral chlorine, for example, methyl chlorine, that chloride is not strong enough, it's neutral. But if it's chloride minus, yes, then it's a strong enough nucleophile. Then it will do this transformation. There's only a handful of atoms that are strong enough when they are neutral. The big ones, phosphorus, sulfur, and selenium, they're big, so they are very generous. They will be nucleophiles even if they're neutral. And nitrogen, like amines are nucleophilic, even if they're neutral. They're even more nucleophilic if they're negatively charged, but even if they're neutral, they are good. And then the leaving group has to be good. It cannot be H or methyl. Never make them leave. It has to be either one of the halogens, or what is this? It's like a man-made group. People made this on purpose. So whenever we have a tosylate in our course, and sometimes you see these in top hat, but tosylate probably the major one, that's an excellent leaving group. And also water. How can we have water as a leaving group? If you take an alcohol, right, that's not a good leaving group. It's not one of those green balls. But if you add acid to it, what will happen? It will protonate. Oh, now it's a good green ball. Now it will leave. Because the rest will be a consequence of this. For example, this one. Some reactions, they are already connected. Imagine a molecule where one side is a blue ball, the other is green. What will happen? We'll have a cycle, right? That's just an extension of that idea. Here's another example. That's also an SN2. Have we seen this before? What was it before? That's an epoxide. So if you have an epoxide, that can be a leaving group, even though it's O- that leaves, but it still happens because the 3-membered ring is not stable, like a spring. So if you have a strong enough nucleophile, it will come from the back. By the way, why does it come this side and not that side? Yeah, that's what we talked about to begin with. That's the nature of SN2. You're looking for the most accessible position from the back, and you attack. And this has to be strong, though. It cannot be water. It has to be either carbon minus, oxygen negative charge, nitrogen negative charge, carbon negative charge. How in the world do we get carbon with a negative charge? It's a Grignard reagent, right? Whenever you have methyl magnesium bromide, that's your methyl minus. Whenever you have phenyl lithium, that's your phenyl minus. That's your carbon minus. And H minus, so if you take LAH, which is lithium aluminum hydride, that will do this. Okay. All these examples, they are attacking a carbon atom. There's more to SN2 than just attacking a carbon atom. For example, you can attack a silicon atom. Don't try to focus on memorizing now. Try to focus on seeing that this is the same SN2 process, where the green ball is left, and which bond will we have now? The blue ball with silicon. Is there any use for that? Is there any use for this thing? Well, now it's a protected alcohol. People use it to protect alcohols because then maybe, let's have it here. Because if that molecule has other functional groups and you want to mess with them, and your reagent will also mess with the alcohol, it makes sense to protect it temporarily so that other reagents will not mess with it. And then you can deprotect it either under fluoride minus conditions or acidic hydrolysis. You can knock it off and it can become the alcohol again. And usually people use like trimethyl silyl chloride, so both of them, all three substituents are methyl groups, and this can be chloride or bromide or iodide, that doesn't matter. But also note that you lose a proton in the process, so you generate some acid. This is why you usually add some mild base to trap this acid. Otherwise that acid will destroy your substrate. So you need something to trap it while it's generated. This is why you will usually see an alcohol, methyl 3 times silicon chloride, and some base. Some more. Look, which atom is this? That's a phosphorus. What can be the green ball? Chloride or bromide or iodide. Any leaving group. Same SN2 happens. But look, the cool thing is that one of those green balls is lost, this one, and now it can see this very complex leaving group that's is a result of those two interacting together. So it attacks it from the back, and what do we have now? Wow! Now we have the green ball that belonged to phosphorus replace the alcohol. How cool is that? You start with an alcohol, and you can have either chloride or bromide or iodide. Because this is an alcohol, this is, I don't know, methyl OH. What do you need to react it with to make methyl chloride? Like, what is that reagent? PCl3, right? If you want the chloride to replace your alcohol. What do you want it to be if this is a bromine atom? PBr3, yes. That's a useful thing. Each time you see an alcohol, you know how to replace it with any other atom, like any other halogen. So yes, there are other, like PCl5, that's okay. If you forget, don't worry about it. Just focus on PCl3 or PBr3. It's very rarely when iodide is used. Now, let's take a look here. Which atom does it attack in this case? Sulfur. Is it at a double bond? Yeah. Is it tetrahedral though? I know you took Gen Chem 1 many years ago, but there is a lone pair in the sulfur which makes it tetrahedral. So yes, SN2 is possible because it's still tetrahedral. The idea is just the same. Why is it useful? Because after this happens, another SN2 is possible, and this again replaces overall that OH for a chloride. What is this chemical? SO, Cl2, right? Because there are two chlorides here. So either you use PCl3 to replace an alcohol for a chloride, or you use SOCl2, and it does the same thing. And that's useful. What is this? That's another tetrahedral sulfur. How did we call it before? This unusual combination of atoms. Tosylate. Yeah, we called it tosylate. So what should we expect based on the same analogy? Is that this chloride leaves, this becomes a new leaving group. This chloride leaves and you have a protected tosylate. And now this is good because this is a good leaving group. So in a way, this combination became your new green ball that you can use later on if you want to replace it in any other process. So one way to make alcohol a good leaving group is to protonate it, to use some acid to make it into a green ball. The other is to make it into a tosylate. Because not every substrate can survive an acid. This one uses a mild base to get rid of this extra proton. Okay, that's SN2. 8 more slides to go. That's SN1. SN1 is easier because it's very rare. SN1 is a very rare process. Look what happened. What's different? It looks like the same as SN2, doesn't it? But what's different about it?
Leaving group leaves first.
Yeah, see how this doesn't attack it. Why?
It's sweet.
Maybe because it can't, maybe because it's too crowded, maybe because of that. Maybe it's just too weak and it can't attack it. But leaving group is still a good leaving group, so it leaves. Does anyone recall what will be the condition, like any solvent that can stabilize the carbocation that's formed? What does it need to have? It needs to have hydrogen bonding ability. It needs to have OH, which is like 99% of the cases. It needs to have an OH, so it's either an alcohol or water or an acid, but it needs to have OH to make this possible. And when you have a carbocation, that will react with everything. Even water will now start attacking your carbocation. Is it still tetrahedral, the carbocation? Is it tetrahedral? With 3? No, how can you be tetrahedral with 3? You need 4 for tetrahedral. So it's planar then, which means will it attack from the same side or from a different side? Well, it doesn't matter, right? It will attack it from both sides because now you're planar, it doesn't matter. This is why I didn't draw bold or dash there, because it's a mixture. You will get, if it was a chiral center, you will lose it. If it was R, you will get 50% of R and 50% of S. That's SN1. Still, it has to be tetrahedral to begin with. You cannot make any leaving group leave from a double bond, like benzene with chlorine. No, that's not a good leaving group. It will not leave from benzene. So it has to be tetrahedral. And it has to generate either secondary or tertiary carbocation. Let's see how much we can remember for this we discussed. Yeah, most of the time when you see SN1, the nucleophile will be your solvent. So if you have, for example, cyclohexyl and bromide, and you react it with water, and you heat it, what will happen? So the leaving group leaves first. The leaving group leaves first. See how here it will make a secondary carbocation. The plus will be in between 2 carbons. So yes, that's okay. Do we have a solvent that can stabilize it? Water, yes. Water has OH. That's good, so far so good. And then water will attack the positive charge. So yes, that's possible. That's a typical SN1. What should we be afraid of whenever we see carbocations? 2 things. Which ones are they? Try to remember. Whenever, not just in SN1, but throughout any other 40 reactions, if you make a positively charged carbon, what are you?
Resonance.
I love resonance. That's good default answer to any question, yes. But specifically to carbocations, what 2 things we always should be cautious about?
Hydrate shift and methyl shift.
Shifts, that's one thing, yes. Methyl and hydride shifts is one thing. Either hydrogen shifts or methyl shifts from a neighboring carbon. Why does it happen?
Stabilize the carbocation.
What's better about this than about this?
More substitutes on neighbors.
Yes, either there's more resonance or there's more substitutions, but this is why it happens. Only from a neighbor. Notice how you show this. It's not that the positive charge migrates here. No, it's this bond with electrons and with the atom migrates here. Same for a methyl. Or, whenever you have a positive charge, E1 can happen. SN1 and E1, they always come together. Let's draw our carbocation. So not only our water will add to this and make an alcohol, but we should always watch out for this E1. So as a side product, one of those protons will be lost because water will also act as a base and steal it. And it will make cyclohexene. Okay. If you have a choice, see how this reminds us that a more substituted alkene is formed. That's called the Zaitsev rule. They always happen together, SN1 and E1. if you heat your reaction, there's always more elimination rather than substitution. But there is one reagent, for example, if you use sulfuric acid or phosphoric acid, and we had a lab on this. Some people are like, what lab? Are we taking lab course also? Like, yes, you do. By the way, the final is coming. But you did have a lab where you used sulfuric acid here on an alcohol. And yes, you generate a good leaving group first, and it leaves to make the carbocation. But the cool thing about sulfuric acid is that it's not nucleophilic enough to add. So you will never have this addition product because it's not a nucleophile, like no. But it will always be a mild base that will help you to make E1 only. So that's a special case, sulfuric acid or phosphoric acid, only E1 or E2 with alcohol, but never a substitution thing. Let's see. Oh yes, that's our favorite. We'll have a lot of it on the test, Grignards. What will happen in the first case? What will happen with the green ball when it reacts with lithium
They will attach you to a carbon and green ball.
instead of the green ball? And with magnesium, then in between. That will be cool. How about this? How is this functional group called when you have a triple bond? Alkyne. So that's a special base. People use it for those alkynes. If you have a stronger base, it will work too. But classically, people use this. That's a base, and it will take the proton away. And in all cases, you will have carbene ions. Yes, the first one is called organolithium compound. Yes, the second one is called Grignard. Yes, the third one is called a satellite ion. But all of them are just messengers. When a postman comes to you, what do you want him to give you? Man, are you interested in anything else from that postman? No, right? That's the hope. So in this, that's the same thing. It brings you lithium, it brings you magnesium, it brings you sodium. You're not interested in that. Their mission is different. Their mission is to supply you with carbon minus. So whatever they carry is what's important. The rest, the metal itself, is not important. So whether this will be sodium or potassium or whatever, or if this is magnesium bromide or chloride, whatever, their mission is to supply you with this part, with the negatively charged carbon, with the negatively charged carbon, with the negatively charged carbon.
Isn't it 2 moles of lithium though? Not 1?
Yeah, very nice, Anthony, very nice. Yes, for stoichiometry purposes, we will need 2 moles of lithium. If you write 2 moles of lithium, bonus points. And their mission of those specific carbon minuses, well, first of all, they're carbon minuses, so they're very strong bases. Do not have water around because they will easily deprotonate water. Like it's a tough reaction. And even if some assignments will try to trick you. I'll try not to trick you. But if you see a molecule where there's some alcohol on the side, forget about what you want to do. The Grignard will react with the alcohol because that's acidic. You cannot prevent that. So that's its first desire. But its love is for carbonyl groups. And the rest of the slides will be how Grignard and all of them react with carbonyl groups. This is why people use it. So whenever you generate them, they're like hunting for carbonyl groups. And epoxides. Well, epoxides we kind of saw on the first slide, right? How Grignard opens an epoxide from the more available positions. But carbonyls we'll discuss here. There is one bonus point here, like one special scenario, and that probably some of you forgot, is that you can take organolithium compound and you can make it into kind of a magical reagent with copper. So once you have lithium and copper, that's like a special postman. He delivers the same carbon piece, so he delivers the same carbon piece, but now this guy's desire is not for carbonyl groups. It can replace any halogen it sees on its way. Even if it's added to a double bond, it will still replace it. Those are called Gilman reagents. They are very, very special. Phenyl bromine. Let's add lithium to it. What will be the product? Phenolithium. Then let's add copper iodide. So this is our magic potion. We will have phenyl 2, copper lithium. This is our Gilman reagent. This is the special postman that delivers phenyl minuses that are looking to replace halogens. So now let's add this compound to, let's make something beautiful. To this baby. You see how it has 3 carbon iodide bonds, even at the double bond. What will Gilman do with this molecule?
Replace it with iodine.
What will it replace? All the iodides, right? All the iodides will be replaced by Grignard will never do such a thing. Organolithium will never do such a thing. They are consumed by carbonyl. They look, is there any carbonyl? No, I'm not interested in you anymore. But Gilman, oh yes, carbon iodide, carbon bromide, carbon chloride, it replaces this by whatever that is. In this case it's phenyl. In this case it's phenyl. In this case it's phenyl. So it's a very useful reagent for that. Now back to Grignard reagents. Ketones have 2 carbons here. What do aldehydes have? So carbon and a hydrogen. Both react analogously. What will be the next product here? Blue ball will add to what? To the carbon. And oxygen will have what? A negative charge. And this thing cannot do anything. Well, it can make the blue ball leave, but it won't really do it because carbon-carbon bond is strong. None of them is a leaving group, so it's kind of stuck. So it will wait before your proton comes and protonates it. That's it. Any ketone aldehyde you take, that's all that happens. It's kind of boring because there's nothing else that happens. The situation will be different if you take an ester. So an ester is when this is what? Like O-methyl or O-ethyl, O-isopropyl, O whatever. Or when it's chloride. But chloride is more intuitively understood as a leading group, like O-methyl is not as intuitive. But esters, think of this ester part as a leading group. So when the blue ball comes, it will not wait for the proton. It will not have time to wait for the proton. It will make the green ball leave first. And what we have again, oh, a carbonyl. So your Grignard will not stop. It loves carbonyls, so it adds to it again. What do we have the second time? A boring part, right? Because it cannot do anything else. So it will be protonated. What's the difference in the big weight, in a big scheme of things? How many blue balls are added to ketones and aldehydes?
1.
And here, 2. It's always the case. And if you use these, then the blue ball is carbon minus. But if you use lithium aluminum hydride or sodium borohydride, then the blue ball is H minus. But the chemistry is the same, whether it's H or carbon minus. Like, that's your blue ball. Okay? Now, look, this is a very useful extension of this addition of organolithium to carbon dioxide. Look, this is just another ketone. If you can think of it as just another ketone. This R minus, the blue ball, adds to that, and then it gets protonated. That's a way to make acids. The trouble with these, what's the difference between sodium borohydride and lithium aluminum hydride? Please don't say one has aluminum in it and one has boron in it. Like, what's the difference in their reactivity? So this will not react with sodium borohydride, but lithium aluminum hydride will react with both of them. You remember that? That's important. Yes, and I think this mentions the same thing. Can we understand this? Try to draw the mechanism for this transformation, and then we will discuss how does this happen. Reacting with Grignard. Yeah, I would say R minus is going to attack the carbonyl group. So that's our R minus. It attacks. What happens next?
Opens it up.
double bond goes to the oxygen. You have an extra lone pair and a negative charge.
Like this?
Yes.
Okay. So that happens. Now, if this was a ketone, so if this was a carbon, then it wouldn't be a leaving group. Then it would just wait to get protonated. That would be the end of story. How boring. But that's an oxygen, so that's a leaving group. So this minus will kick it out. How can we show it though?
The lone pairs going to the carbon. The lone pairs of the oxygen with the negative charge.
Yeah, we need to show somehow. This, right? This? Okay. So, makes our... Anything missing here? There is a carbonyl, yeah.
So you add another same process
Huh?
on the oxygen.
Do we care about charges?
Yes.
We do? Right, of course. That'd be a huge mistake, like the end of the world, if you don't show that minus. You cannot lose a charge. You have to, same in resonance, same in any reaction in the world. If this is negative, you have to generate something negative. So in this case, it will reside in oxygen. But we have a carbonyl, which means our minus, which we have a lot. I mean, imagine yourself adding it with some syringe into your reaction. There's a lot of it. You don't add just one molecule. There's like billions of them around, so you always have a lot of R minuses around. And this will add again to a carbonyl. This again will break. Right. And now this is where our second R is. And does it have a leaving group now?
No.
No. So it's kind of stuck. It will just wait before you add some acid to it, and this gets protonated. Oops. Like this.
Yeah.
Now imagine, are we on the same page? Imagine instead of this, we're taking sodium borohydride, sodium BH4. Would the same thing happen with sodium BH4?
That wouldn't work.
Right, because that's an ester. Sodium BH4 doesn't react with an ester, right? But imagine you take this and lithium aluminum hydride. So you take this and LAH. Would the same thing happen? Only that this R is your H now. Right? Same thing happens exactly. It's just instead of the R, that's your H, your H minus from LAH. Does this make sense?
Mm-hmm.
Okay, that's good.
I have a question. Why do we make the oxygen leave? How's it leave?
Why this happens?
No, like why did that oxygen leave? Not
The-
that one, the other one at the bottom, the right. Yeah.
Why does it leave here?
Yeah, why does it leave?
It's a very legit question. First, because as far as charge, it's the same, O minus, O minus. So we're not gaining anything in terms of, oh, we suddenly get rid of charge. We don't, right? There's O minus here, O minus there. This is a rare case where entropy is the only driving force, because this is more organized, that's cyclic. There's a lot of order here. That's more disorderly because you break it. So that's the driving force in this case. Now, what is it? This is acid and base. How do you call that green ball with an H? In a scheme of things, look, it transfers that H to the blue ball. The blue ball comes and takes the H. How do you call the green ball with an H then? And how do you call the blue ball? Look at this. That's a very basic question. Something takes an H from something else.
It's base.
It's a base.
Yes. So how do you call the green ball with an H?
Because it's an acid.
That's an acid. Yes.
Yeah, because it's the thick version C all the bromine.
Yes. No matter how complicated those blue and green balls are, this is what we call them based on what they do. There are some popular bases in this course that we need to know. In reality, there are millions of them, but there are some very popular ones. For example, the sodium amide that we know is used for alkynes only. Well, in our course. Sodium hydride is another base, and that's used to deprotonate alcohols. So if you want to deprotonate an alcohol and to make O minus from your alcohol, take sodium H. That's a good base for that. Triethylamine and pyridine, they're used just to trap some HCl produced. Maybe you recall when you put silicon on, or tassel chloride when you react with it, you use those very mild bases. just to trap the resulting acid. And then of course, Grignard and lithium, organolithium compounds are very strong bases, so just beware that whenever you use them, if there's anything acidic around, they will easily deprotonate it. For elimination, these are the ones that you use in the course. OH minus, or methyl minus, or ethyl minus, terbutoxy. They're so similar to one another. This one kind of stands out because that's very crowded. But these ones, there's basically no difference between them. They're about equal strengths. And yes, in real life, whether it's sodium or potassium counterion, that doesn't matter. So if you take sodium methoxide or potassium methoxide, they will react the same. What is their job? What is the job of every blue ball on this slide? To steal a proton. That's what they're used for. These ones can also be nucleophiles in SN2, so please don't forget that they're still good nucleophiles because they're not hindered. This is too crowded though, so this is only used for eliminations. Potassium terbutoxide, only for eliminations because it's too crowded. And there's one other thing, if you remember that one, you were like, amazing. Potassium terbutoxide, if you have a choice between alkenes, it results in the least substituted alkene, which is counterintuitive. So that's like a very exceptional thing. We call it Hoffman product. That's the one that makes a Hoffman product. That's a very bonus type thing, if you remember that one. Okay, now acids. Sulfuric, HCl, HBr, H-iodide, strong acids. Can protonate alcohols. HBr and HI are so strong they can even protonate ethers.
Wow.
I know, that's so unthinkable. And then H3O plus, some people are so confused by this H3O plus. All that is in real life is that you take some HCl and you dilute it in water. That's your H3O plus. So you take some dilute sulfuric acid. Another important slide that I think goes through the whole course, and sometimes we don't notice it. Never stop your reaction at a charged molecule. Please don't. Nature will, or chemists will try on purpose to generate neutral molecules. So do not leave your reaction like this. What's the simplest way to make this neutral? Steal a proton, take some solvent, steal a proton, you have a neutral alcohol. That's good. That's not good either. What's the simplest way to get rid of charge? To steal an R or to steal a proton? Proton. Like exchange of protons is super easy. That's acid-base chemistry. So usually solvent, water or alcohol will be enough to do that. Whenever you have Grignard reactions, usually you arrive at those alkoxides, O minuses. How can you make them neutral again? Add some acid and it will protonate it. But always make it a goal to make them neutral. See how neutral, neutral, neutral. All organic structures in the end that you isolate should be neutral. That's a good thing. It's very rare when people on purpose generate charged molecules. Okay. Elimination. What does this mean? What's special about H and the green ball here? Yeah, they have to be like anti to each other. This classic E2 will not happen from any other conformation. It has to be anti to each other. And when that happens, look, the purple balls, are they pointing your way? Both of them? Are both of them bold? Well, yeah. Yeah, look, this is bold and this is bold. This is purple and this is purple. So they are pointing both your way, which means they will stay pointing the same direction in the alkene. In the alkene, they are cis to one another. Same with orange balls. Look, they are pointing away from you, which means that in the products, they will still be pointing the same direction to one another. They will be cis to one another. And elimination generates double bonds, of course. So the only requirement is that the blue ball has to be a strong base. There's more substituted alkenes produced, just like Zaitsev product. Let's see what else. Same will happen. Look at this unusual case. This is what relevant for your test. If you have two bromines on the same carbon, for example, or two chlorines, or two whatever, you take a strong base. Which one? What would be a strong base based on the previous slide? NaNH2, or potassium terbutoxide, or I don't know, KOH. So you take the first HBr away, and you make an alkene. But you use it again, That's another HBr taken away. This is how you make alkynes. So by using the E2 twice, you can make alkynes. Yes. Let's see. If you do the same elimination on an alcohol, so if you take an alcohol and you replace this H with a green ball, then you can eliminate them and make a ketone. Note that you cannot do the same on a tertiary alcohol. Why? Because there's no H's here, right? There's no H's. So this is stuck. Never oxidize tertiary alcohols, but you can easily do this. And which oxidants? Do you recall any oxidant that will do this? What can you take to add to an alcohol to make it into a ketone? What is this oxidant? Any memories? And we will discuss this. We'll refresh this. But look, the situation with primary alcohols is a little more complex. The first step is the same. But what happens here is that an aldehyde sometimes adds water to it, and there's an opportunity for the second loss of water and making carboxylic acids. So some oxidants are very good at both of them, and some are very good in stopping it at the aldehyde position. Does it make sense? So maybe with examples it will make some sense. But the harsh oxidants is chromium. They are chromium based. Maybe H2CrO4. They are the harsh ones. They are the ones that will go all the way to carboxylic acid if you have an aldehyde. And some are mild. Which ones are mild? Do you recall which ones are mild? BCC, yes. So these ones are from the mild group. It's good to keep them separate in your boxes. One is very harsh, the other is mild. Let's do an example here. Let's say you have this alcohol right here, and this alcohol, and maybe this alcohol. It's a molecule that has all kinds of alcohols in it. If you take PCC, which one is this one? Mild one or harsh one?
Mild.
Mild. So it's looking for alcohols and it's trying to steal hydrogens in such a way that a double bond is formed. Will anything happen to this part? Because there's no hydrogen here, right? It's done. Will anything happen to this alcohol? Because there is a hydrogen here. So if you take this hydrogen and this hydrogen, you will have a double bond right there. Let's draw this. So you will have this. How about this alcohol? Will H and H be taken away? Yes, so you will have an aldehyde. Does it make sense? So that's PCC. What if you take the harsher one, for example, H2Cr2O7? That's the harsh one. What will be different? You will almost have the same molecule, but there will be a difference. What will be different? Yeah, what will not survive is the aldehyde. Harsh oxidants oxidize aldehydes all the way to carboxylic acid, so don't keep it an aldehyde. It will be a carboxylic acid. And yes, there are replacements. You don't have to use this all the time. You don't have to use PCC all the time. You can see PCC can be replaced by those complex ones. Try to remember their names. Now, probably my favorite slide. Look, what will happen here? If you have hydrogen and a double bond, what will happen? In presence of palladium. It will add from the same side or different sides? From the same side, that's right. What if we do this on a triple bond? Then it will add twice. But there is a catalyst that's called Lindlar's catalyst that stops after adding just once. And what is special about this catalyst? It's like poison palladium catalyst. If you write poison catalyst, that's fine. That would be fine. So you add it just once. Try to remember that adding BH3 is just the same deal. So BH3 is really a hydrogen, only that one of those brown atoms is replaced by BH2. And if you have a choice, and boron is big, will you go toward the carbon that's more substituted or toward the carbon that's less substituted? Less. Yes. And then comes this magic box. This set of reagents, all it does, it converts BH2 to an alcohol. Look, the overall result from this scheme is that water, H2O, is added to an alkene in such a way that OH is far away from substituents. And chemists call it anti-Markovnikov. Same happens on a triple bond. Don't look here. If you were boron, would you add to this carbon or the left carbon?
The left.
Well, you are crowded. Will you add away from that substituent, closer to hydrogen, or closer to that carbon? The hydrogen. Because hydrogen is small. So boron will add, yes, away from that carbon. H will add closer to the carbon. This is a set of conditions that replaces boron for OH. Same idea. The difference is that these are not stable because of this double bond. Alcohols are stable, that's fine. But these are called enols because they are at a double bond. And what happens with them is called tautomerization. How can we remember what happens? Double bond moves where? This double bond migrates.
Moves to the OH, the alcohol.
Becomes a carbonyl, right? And this H migrates over there, and that's what happens. Anti-Markovnikov addition of water. Okay, let's see. The only an obvious reaction from this slide to make it very complete is, since this reaction adds hydrogen from the same side, this reaction is complementary to that one. It allows to add hydrogen from different sides. Do you recall what the set of conditions is? Most people don't. It's at -33. It's a hard reaction to perform in lab. Yes, it's lithium or sodium in liquid ammonia. So that's a hard one. If you remember this one, that makes a complete package. I encourage you to remember these reactions as one package, like a bundle, because they are related. Even though they're in different chapters of the book, they have very similar reactions in their heart. Okay? Well, that's a short slide. What does this proton want? Electron. If you were this proton, will you add to this carbon or that carbon? Like the bottom one or the top one?
Top one?
Well, if you add to the top one, your plus will be here, tertiary. If you add to the bottom one, your plus will be primary. So which plus do you want, primary or tertiary?
Tertiary.
When you're sad and lonely, do you want more friends or less friends? More friends. So is with positive charge. So you want the tertiary positive charge. And then if this is HBr, then of course the blue ball is Br. If this is HCl, then the blue ball is Cl. If this is Hi, then the blue ball is I minus. If this is H2SO for water, then the blue ball is water. If this is mixture of sulfuric acid and alcohol, then the blue ball is alcohol. So then the blue ball adds to that positive charge, and here you have it. See how this can be many different variations, but you have to recognize that all of them have a proton and the nucleophile. If you see H2SO4 water, then what will be your nucleophile? Water. If you have H2SO4 and isopropanol, what will be your blue ball? Isopropanol, yes. What if you have HBr? What will be your blue ball? Br, yes. Okay. We got this, no? Yes?
Yeah.
See how people call it? They call it Markovnikov because the blue ball adds to the more substituted carbon, so people call it Markovnikov addition. And of course, the tricky part to make it a complete package is to know how to add HBr. That's the only chemical that works. None of them can add anti-Markovnikov, but this one can. Is how to add anti-Markovnikov. What stands in between? What set of conditions allows us to add anti-Markovnikov? So if you just mix them, it will of course function as this, and it will add Markovnikov. So there must be some additive to this to make it add anti-Markovnikov.
HBr and water.
So She said
No,
that
then
would be
it's
amazing.
just, then it becomes one of them. Some unusual additive. Anybody remembers? What is husband's name of Beyonce?
Jay-Z.
How do you know that? And then you don't remember peroxide. So you,
How do you want me to know that?
you remember Jay-Z?
Jay-Z is easy to remember.
That's two. That's easy to remember. That's a peroxide.
She said peroxide.
Yes, I know. This is amazing. But not everybody else. Not everybody else said peroxides. How did you remember that, Leslie? You just remembered. You studied, yes. Peroxides. Not hydrogen peroxide, by the way. So many people put hydrogen peroxide on top, on like exams or quizzes. No, try to use some organic peroxides. Anything. You can write ROOR. Peroxide. Okay, so that's this. Now this slide might look overwhelming at first, but all that is, my hope is that it will clarify so many complex reactions for you. Try to focus all your energy in hope to understand this slide, because this can explain three very complex reactions. Look, if this is bromine, so Br2, then one of them is bromine, the blue ball is bromine also, right? If Br2, there's only two bromines, right? So one is red, the other is blue. So same with this, if you have bromine, one is red, the other is blue. What happens when the angry bromine, so bromine plus wants electrons, it makes a three-membered ring that's called bromonium cation. And that three-membered ring, as you remember, is not stable. So the other blue ball, just like before, the Grignard did, it attacks it from the back and opens it up. That's why it's anti. That's why bromine adds to alkenes from two different sides. Because the first one makes a three-membered ring, the second one opens it up. That's why it's anti-addition. Does this make sense? Bromine and alkene. What's the motivation here? Like, why is this bromine plus? Why does he want electrons?
Because
it's
he's
plus.
positive.
Plus means it wants electrons.
He's hungry.
Of course, normally we don't think of bromine as like bromine plus, bromine minus. Like we think of it as non-polar. But in reality, they are always in fight for their electrons. One of them will have slightly more than the other at any given point of time. This is why we can represent it as one being positively charged, the other negative charge. Okay? Now imagine if you have mixture of bromine and water, then what's the blue ball? Water. What if you have bromine and alcohol? What's the blue ball then? Alcohol. Right? So see, in all these combinations, this will be your source of red ball, that's your bromine, the one that adds first. And then water, alcohol is the one that attacks it from the back. And this is how you have more complex substrates. And yes, people can confuse you by saying NBS. NBS is a safer version of bromine, or NCS is a safer version of chlorine. Same idea. So in this case, your red ball is still bromine. In this case, your red ball is still chlorine. If you have NBS and sodium chloride, what's your blue ball? Chloride. Okay? This gives you a lot of opportunity to add two different atoms to a double bond. Now look at this. What is this red ball? Mercury. So mercury does the same thing. You take mercury acetate, that's your mercury. It makes a three-membered ring, and then water opens it from the back, and you have you added OH to your molecule. Do you recall how to get rid of mercury? What reagent do you need to add to replace it with a hydrogen? That was quick. You sure?
No, I don't know.
Okay, who's sure? What do we need to add to get rid of mercury?
NABH1.
I know, I heard that. But I need some more votes. Do you trust Christina?
Sure.
Yeah. So, okay. Now, if you take mercury and methanol, then what's your blue ball? Methanol. Right? If you take mercury acetate and ethanol, what's your blue ball? Ethanol. Right? This gives you opportunity to make ethers, right? If you take methanol, you will have methyl ether. If you take ethanol, you will have ethyl ether. Look how similar they are. Of course, they are in different chapters in any organic chemistry book, but it's a very similar process. Same happens when you well, it looks a little more complex, but that's MCPBA. All that is, kind of a similar thing. One of them is red, but there's no blue ball, so red ball just gets stuck. And this is how you make epoxides. That's your favorite reaction for a lot of you,
Yeah.
right? So, and you can stop here, right? Usually you add MCPBA, you get your epoxide, that's it. But what will happen if you add acid to that epoxide?
Open it up.
Protonate it, and then it is activated. Now the blue ball can attack it. Now, notice a very curious thing, Look, which position does it attack? The more substituted or less substituted? But that's different from what we saw on the first slide. There, Grignard attacked it from the less substituted position, right? The more available. Why in the world does it attack it from the more substituted position?
Basic conditions.
So if we react with the hydrogen, if it's
Basic
on the other
conditions.
side.
Because it's now under acidic condition, it attacks it from a more substituted. That's also hard to remember, but try to remember this. And see how all three reactions are related here.
Wait, so wait, what does say basic then?
Compare, because compare means under basic it attacks it from the other side.
Which is less substituted.
Yes, yes.
It's acidic, but it says
So compare with
with
this.
basic. Yeah. Okay.
So it's like, hey, look at this, it attacks it from the more substituted side, and compare it with the basic conditions when it's attacked from the more available side. I think we have 2 more slides if I'm not mistaken. Do you recall this? This is a reminder that you can, similar to epoxides, you can make 3-membered rings by adding carbenes. So there are 2 reaction conditions. One adds CCl2, the other adds CH2. And finally, these are our scissors reagents.
I like those. They cut.
Remind me,
Cut it.
how
Cut it.
do we cut a double bond and put oxygens there? What is this?
O3 together.
That's ozonolysis.
I like that.
How do we cut it in such a way that aldehydes get oxidized into carboxylic acids?
4.
Nice.
I remember that.
How do we add OHs to both sides of the double bond?
Cold chemical.
Gold came in for water, or osmimo for hydrogen peroxide. Now this is a very tough question. How do we cut this bond in cis-diols, super rare reaction? That will not be. Yes, periodic acid. That's right. So that's right, periodic acid. That's a rare one. It's okay if you don't remember this one. Now, this is ozonolysis, and yes, hot chemonophore will oxidize aldehydes, and this into carboxylic acid. Similar thing with alkynes. Cold chemonophore makes those diketones. How can we cut this bond completely? Well, let's use hot chemonophore, or let's use ozonolysis. By the way, this is all there is to know about organic chemistry reactions, like all